Okay, since nobody has joined, I'll start and the recording will be available. So let's begin. Mm, okay, so today we'll be discussing CDMA, also known as. So we were already discussing some aspects of CDMA in the previous session, but yeah, we have some more discussions this week. And so CDMA stands for, as we know, Code Division Multiple Access. So this is covered in week 11 of the course in the corresponding lectures. And so this is the second last tutorial session, and the last one will be this Sunday on mine. So anyway, let's solve. So most questions are from this kind of noted down. This is a slightly involved topic, so you'll find most questions from lecture. So most of the questions are multiple choice questions in this week's assignment, and they are directly derived from the lecture. So I'll try to not do them because you'll directly find answers to them in the lecture notes itself. So there's and avoid discussing them, and instead I'll focus on questions that require some kind of numerical computation that might not be directly evident from the lecture, and so I'll focus on those. And if time permits, I'll discuss some other topics or if there are any doubts by any student joining me. So let's start. So let's say we have a two-user CDMA system, and it has imperfect power control. So you don't have power equalization across the users. So that means there will be some interference. Imperfect power control. And so and you are provided that the channel coefficients for the users. For first user, channel coefficient is, let's say, 0.5. And for the second user, let's say this is 2.5. All right. So this is the channel coefficients for both of the users. And you're told that the CDMA, the SNR for AWGM channel, which is ED by N naught, that is equal to, so let's say, so let's say this is equal to 3 dB, right? ED by N naught, this is equal to 3 dB, and the chip coefficient Q is equal to it's 32, right? So this is the number of chips for the seed, like for that gold sequence. And so you are asked the values, you are asked to compute the degradation factors for user one and the degradation factor for user 2. You're asked to compute these values. So how we do that? So if you remember, so the degradation factor is essentially what we multiply to the SNR. So the degradation factor for the user 1 is essentially this quantity 1 by, so we can see the formula from the lectures. This is essentially if we kind of, so we have signal power and we multiply it with the degradation. We have the AWG and SNR, and then we multiply it with the degradation factor to get the actual SNR. So you can compute this to be EB by N naught times 1 by Q times mod of alpha 2 squared. Right? So this is the degradation for user 1. Just a second. And similarly, degradation factor for user 2 will be 1 by 1 plus EB by N naught 1 by Q times mod of alpha 1 squared. So this is very easy. You just have to put the formula and solve. The only thing you need to be careful about is that EB by N naught is given in the dB scale. So in dB scale, so you have to be careful about that. So what does 3 dB? So because all of the quantities are in linear scale. So 3 dB, 3 dB is approximately equal to 2 in linear scale. Just writing it in brackets. So this is approximately equal to 2. So let us just substitute the values, and 1 plus 2 into 1 plus, 2 into 1 by 32 into 2.5 squared. And likewise, this value will be 1 by 1 plus 2 into 1 by 32 into 0.5 squared. And so these values can be calculated. And I have cooked up the numbers. So I don't know. Hi, Anand. Somebody is on. Can you hear me? Hello.
Hello, sir.
Hi, can you hear me?
Yes,
Okay.
sir.
Okay. So I was waiting and waited for 10 minutes and nobody joined, so I started. But since you have joined, so I can kind of start from the beginning again. So so this week, the topic that was being discussed in the lecture was CDMA mainly. And so I looked at the assignment, and most of the assignment questions are just MCQ questions straight from the lecture notes. So so that makes it really easy, and you can simply refer to them and answer them. So I'm trying to focus on those questions that need some kind of numerical computation, and so I'll focus on those kind of questions. Or if any other doubt you have, I can try and clarify. That is one thing. So I started with this first question, where uh, you have a two-user CDMA with imperfect power control, and 1 second. By imperfect power control, we mean that like there is like interference cancellation, etc., is not perfect. So the signals, the users interfere with one another. So So when we are considering first user, then the second user is an interfering signal, and when we are considering second user, then first user is an interfering signal. And so so the interference coefficients are kind of given here. So it is also there in the lecture. So for user 1, this interfering coefficient mod alpha 1 is given as 0.5. For user 2, this is made up values, but anyway, just user 2, it is 2.5. And you are told that for AWGN channel, SNR, the AWGN channel SNR is nothing but the energy of one bit divided by noise power. So that is EB by N naught. That is given to be 3 dB. And in CDMA, as we know, we have these gold sequences or Kasami sequences, and they have a certain length, capital Q, so the chip length. And so that is Q given as 32. So with that, you have to calculate DG1 and DG2. So these are the degradation factor for user 1 and degradation factor for user 2. What is degradation factor? Degradation factor is this. So the formula is there from the lectures, but essentially it is the factor that we multiply to the AWGN SNR to get the actual SNR. So the actual SNR is nothing but EB by N naught times DG1 for user 1 and EB by N naught times DG2 for user 2, right? So so then the calculation can be done. It can be shown that for DG1, the formula for either of the two users, the formula is 1 by 1 plus EV by N naught times 1 by Q times the mod of the other users interference, this factor, other users correlation factor times squared. So then this just becomes an exercise of just putting the formula. It is very simple. The only thing you need to be careful about is that this EB by N naught value is typically provided in dB. So you need to convert it to linear scale. So that is what I did. 3 dB is almost equivalent to 2 in linear scale, 1.99 something. So it's 2. So you can just put the values and then calculate. There is nothing much to be done here. So is this clear?
Yes.
Any doubt? Yeah.
No, sir. This is given in solution, sir. So we refer.
Yeah. Okay. Okay.
Only,
Yeah, I
sir.
think similar.
What is exactly degradation factor, sir? Why it is called degradation factor?
Degradation factor is because, see, this quantity is obviously 1 by 1 plus something. So you can see mathematically that it is less than 1. So that means that what will happen if you multiply a quantity that is less than 1 to another quantity, then it will reduce the value, right?
Yeah.
So this factor is called degradation factor because it reduces the value of the SNR. Like for an AWGN channel, your SNR would be EB by N naught for just AWGN channel. But then you have to multiply this factor to account for the degradation in SNR because of interference. Does that make sense?
Okay, means its value is less than 1, sir.
Yeah. So its value is less than 1. So then what happens is, then let's say this value is 0.7. So that means there is like your SNR has become 70% of what it would be without interference. Does that make sense? Like if there was no interference, then its SNR would be some value EB by N naught. And because of this degradation factor, it has become like 70% of what it would be. Or like there is a 30% degradation, whichever way you call it. So yeah, that is why it is degradation. Does this make sense?
Okay. Okay, sir.
Okay. Let's continue. What else? You can calculate. So now you are asked what is the, so this is degradation factor, and then you are asked SNR, SINR 1 for user 1 and SINR 2 for user 2. So how will you calculate this? So as I said, like see, SINR 1 is firstly the kind of channel gain kind of term comes first. So channel gain of user 1 times AWG and SNR EB by N naught times degradation factor DV1. So this is why this is degradation factor, because this quantity is less than 1, and this indicates the impact of interference on the impact of interference and noise on the SINR, right? The impact of interference, to be specific. Okay. So this is less than 1. And so again, this is just put the formula and do. Similarly, SINR2 equal to mod of alpha 2 squared. So the channel gain of the second user times EB by N naught, which is AWG and SNR times DG2. This quantity is also less than 1. So what you have to do is just calculate these DG1 and DG2 and put it here. And we also know the other values, right? Alpha 1, alpha 2 is known, EB by N naught is known. So if you just put and compute. Okay. And then you can calculate this. I can calculate and show, but I think it's pretty simple. Just have to put in calculator and solve. But this is the method, right? So actually, like maybe if the degradation factor doesn't make sense, let us just multiply it, forget the nomenclature, and let us see what the SINR expression looks like. So this is mod of alpha 1 square EB by N naught divided by, now what is degradation factor 1? This is 1 by 1 plus EB by N naught 1 by 2 alpha 2 square. So 1 plus EB by N naught. So I hope this now looks familiar, right? So let's say if you normalize with noise power, so your normalized noise power is 1, and this is your normalized interference power, this term, and in the numerator you have normalized signal power. So this is signal to interference plus noise ratio, SINR. It's just a different way of writing the same thing.
Sir, please repeat. Can you repeat, sir?
Yeah. So let's say I just put the formula of DG1 from here to here. So this expression is familiar, right? This is signal power. Like it is just I'm just using normalization factor of N naught. So dividing it on both sides of numerator and denominator. So this is normalized signal power, right? Numerator.
Alpha 1 square.
Yeah, mod alpha 1 square times the AWG and SNR, right? This is like the channel gain. Mod alpha 1 square is channel gain, and this is AWG and SNR, right?
EB by N naught is AWG and SNR.
Yeah, this is AWG and SNR, right? Like we don't know the AWG and what is AWG and channel. AWG and channel is Y equal to X plus some noise. That's it. So there is no channel gain here. So if you multiply this channel gain alpha 1, then you get this mod of alpha 1 square, right? And now you have, now you also have interference. So you have another alpha 2 y1, alpha 1 x1, alpha 2 x2 also. So then this interference term comes here. So this is signal power, right? This is signal power. This term is interference power. And this term is noise. So like normalized noise. So I've just divided by noise variance throughout. So this is SINR. So this is just a different mathematical way of writing that so this thing is the degradation factor, right? This whole thing is the degradation factor.
Sir, so, what you said, alpha 1 square is what?
This is channel gain, right?
Channel gain, alpha 1 square.
Yeah.
Yeah, okay.
Yeah, this is a channel game because like sorry, 1 second. You have this kind of channel, right? Uh, 1 second. 1 second. You have this kind of channel, right? Y equal to alpha 1 x1 plus alpha 2 x2 plus n. So that is typical interference channel. So this is your direct channel gain. This is your interfering channel gain. This is your noise part. So that is all that is there here. So you have AWG and SNR. You multiply that with channel gain, which is mod of alpha 1 square. So this is signal power. And then you get interference power in denominator and your noise is 1. So this is the SINR expression which we all know. Now you can write it in a different way. You can say that, okay, this is my, like you can say that this is my actual, actual SNR if there was no interference. So if there was no alpha 2, if there was no interference, then I would get this SNR, mod of alpha 1 square EB by N naught. Because of interference, I have this degradation factor DG1, which is calculated like this. So that is the role of degradation factor. So this degradation of signal 1's SINR happens because of interference caused by user 2. And similarly for user 2, degradation happens because of user 1's interference. So that is the whole idea. Is this clear?
Yes.
Yeah. The rest is just doing for just putting formula, right? So let's see, one more person has joined. Do you want me to repeat instead of single? I can quickly repeat. Maybe or I can come back to this later if that is fine.
Yeah.
ZTL single is there. Let's see. Let's go to the next problem. Actually, related problem only. So now very simple question can be asked that let's say if I increase alpha 1, let's say alpha 1 increases, then what happens to SINR 1? Does it increase or decrease? And what happens to SINR 2? So can somebody tell me, does it increase or decrease?
Yes, sir.
SINR 1.
1 will increase.
So yeah, this increases. This is correct. And for SINR 2?
SINR 2 will decrease because SINR 1 is increasing.
Yeah, I mean, partially correct. So SINR 2 will decrease. SINR 1 will increase because clearly we can see that mod alpha 1 square will increase and so it will increase. SINR 2 will decrease because of the degradation factor. So degradation happens because of interference. And so if we increase alpha 1, then this degradation factor becomes lower because of increased interference. And so then this decreases the SINR. So yeah, like intuitively, what this means is that you are helping user 1 and harming user 2. Similarly, you can also think the other way. Like, so this is one small problem. And this is there. Any questions? Okay. Now I'll solve this kind of off-topic question that is there, but it's very calculated. So I'll solve that first. Okay. So you are told that there is a base station, right? There is a base station, let's say, and so one base station, and there are two users. So the system has, let's say, a downlink system. I can just maybe draw it. So you have one base station, and then you have two users. So this is user 1 and user 1, and this is user 2. Right? So this use, sorry, 1 second, U1 and U2. And so the base station needs to communicate to both, right? And so it uses, so this is essentially what we have is downlink CDMA system. So it will use two different spreading codes, right? So I'll just keep it simple. So it uses two different spreading codes, C1 and C2 for user 1 and user 2. And C1 and C2 have to be orthogonal to each other. So let us say C1, this code is 1, 1, and C2 is
हाँ नहीं सर, मैं
1
इधर
minus 1.
बता दूंगा, वो वहाँ स्टूडेंट के साथ
Hello?
मैं इधर आपको
मेरे को मत बताओ, स्टूडेंट को
नहीं, स्टूडेंट को नहीं, मैं आपको बता दूंगा।
ये
Hello, could you mute please?
सॉरी सर, देयर वाज इंटरफेरेंस।
Okay. So C1 and C2, as we see, orthogonal codes, because if you multiply C1, if you do dot product of C1 and C2, you can see it is 0, right? So C1 and C2 are orthogonal codes that are being used to send some information. And so I'm just showing the process so that you can kind of do it for your assignment also. And you have a multipath channel, right? Channel is let's say similar for both users, and multipath channel, and the channel is given, so in time domain representation is given, the channel is something like 0.5 and minus 0.4, let's say, something like that. Two-tap channel. You have a channel which behaves like this. So now let's say you are told that base station transmits xn equal to C2. So what is C2? 1 minus 1. So the base station transmits this thing. And so what you want to figure out is so what happens now is that the base station transmits, sorry, my bad. I wrote it in the wrong way. So the base station is transmitting C1 to both. So the user 1 has its own code, designated code known as C1, and user 2 has designated code C2. And the base station is actually transmitting C1 to both of them. And now what will happen here is that this signal which has been sent, sorry, I have written C2, right? So the base station transmits in this case C2 to both of them, C2, C2. And so what will happen now is that the signal, the signal will interact with the channel, and so there will be convolution in time domain. And then at the receiver end, there will be some unscrambling at the receiver end, right? So there will be some correlation with the receiver end, and then the user will decide whether it is receiving C1 or C2. So we have to compute that correlation. So how do we do that? So the first thing that we have to see is the receipt signal at both the users. So, okay, so let me first write the question. So question is, correlation at user 1 and user 2. 1 second. What happened here? And user 2, right? Okay, I see some mess. Let me clear it up. Okay, this is not perfect.
Excuse me, I
Just
have a
bear
query.
with me. User 2. So correlation at user 1 and user 2, you have to find out. So first thing you have to find out before computing correlation, you have to find out receive signal, right? Receive signal at both users. That is nothing but xn convolution with hn. So this you have to compute. So we'll have 1 minus 1 convolution with hn, which is 0.5 minus 0.4. So how do we calculate convolution? This is, I think,
Sir,
basic.
excuse me.
Yeah.
Sir, from where we have got this 1 minus 1 for C1 and 1, sorry, C2 and 1 for C1?
So this is told to you. So this is given in the
Okay.
question. So this is, so
Okay.
essentially what you will have is, what you need to have is, the user should have orthogonal codes. So if you multiply C1 and C2, it gives you 0. So that is the whole idea. So if you maintain that, you can write any code.
Okay,
I'm just
okay.
like,
So will it be
one-
given in problem, sir, or
It will
we
always
have
be
to
given.
assume it?
No, it will always be
Okay.
given.
Okay, sir.
Or maybe you will be told that it is a 2-dimensional orthogonal code. So then this has to be 1, 1 and 1 minus 1, because there is no other way. Or like, you can
Okay.
also do 1, 0 and 0, 1. That is also fine. So then, but typically you will not be asked to assume or anything, you will be given. So
Okay, and what about, sir, this 0.5 and minus 0.4? H of
this
n?
channel will also be given. You will always be given channel.
Okay, this will also.
So this is
Okay,
channel,
okay,
which I have just taken some values. It's just hooked up, but channel will also be given. So
Okay,
what
okay,
is important here is the process. So receipt signal is yn is xn convolution with hn, right? So okay. So what is yn? Yn we know is summation k equal to 0 to n minus 1, something like x of k, h of n minus k, right? Something like that. So let us see. And this is for n equal to 0 till capital N minus 1. And what is this capital N? Typically, this capital N is, 1 second, sorry. Typically, this capital, or like actually, let me use L, capital L, then it is more like intuitive. L minus 1. Or okay, no worries, no then. So this n is typically for linear convolution, it is n1 plus n2 minus 1. So here n1 is length of first sequence. So xn is of length 2. So we can see n1 is equal to 2. And n2, hn is also equal to 2. So this is 2 plus 2 minus 1. So this will be 3. So there will be, essentially, this is you will have n equal to 0, 1, 2, 3. So let us take n equal to 0. So what is y0? Y0 is summation k equal to 0 to 3 x of k and h of minus k, right? Because n is equal to 0. And now let us see h of n. So for k equal to 0, x of 0 is 1. And similarly, h also, if you put 0, you will get h of 0, so that is 0.5. For k equal to 1, so let us just keep writing. So for k equal to 1, you will see that we'll get h of minus 1, which doesn't exist. So whatever doesn't exist, you will assume it to be 0. You will assume 0 padding on both sides for both the signals. So if you assume 0 padding on both sides, then essentially for 1, 2, and 3, you will see that you will get h of minus 1, minus 2, minus 3, which doesn't exist. So it's everything is 0. So you have this one term essentially, which is x0 times h0. That is 1 into 0.5. So this answer is 0.5. So this is just again basic Fourier transform kind of thing, like digital Fourier transform, and like digital convolution essentially. Similarly, if you put y equal to 1, then you will have x of k, h of 1 minus k. So if you put k equal to 0, you will get 0.5. You will get x of 0, 1 times h of 1 minus k, which is h of 1, which is 0.4, right? Or minus 0.4. So this will be minus 0.4 plus you will get one more term, which is x of 1 minus 1 and h of 1 minus 1, which is h of 0, which is 0.5. So minus 0.4 and then you will have minus 0.5. So this will give you minus 0.9, right? I hope I'm doing it right. Okay. So this will give you minus 0.9. Similarly, if you do y of 2, then what will happen is yeah, 1 minus k. So, so y of 2, yeah, y of 2 will give you, let's see, summation k equal to 0 to 3, x of k, h of 2 minus k. So for k equal to 0, h of 2 doesn't exist. H exists only for 0 and 1. So that doesn't contribute. For k equal to 1, we'll have h of 2 minus 1, which is 1. So this will be 0.4. So then that will be x of 1, which is minus 1 times minus 0.4. So this will be plus 0.4. And again, for k equal to 2, you won't have any x. So x doesn't exist beyond 2. So then this is y of 2. And then then the final term, which is y of 3, will probably be 0. Let us see. X of k, h of 3 minus k. And so for k equal to 0 and 1, we'll have h of 3 and h of 2, both of which don't exist. So both of them are 0. And for k equal to 2 and 3, x of k doesn't exist. X of 2, x of 3 are 0. So this will come out to be 0. So what we have essentially as output is, so your received signal y is equal to y0, 0.5, y1 minus 0.9, y2, 0.4, y3, 0. I hope this step is clear. Any problems with this? It's just convolution calculation. Okay. If this is fine, then now the next step here is my bad. And now the next step here is to do a correlation with both of the scrambling sequences, right? So what will happen here now? So for user one, correlation is y times correlation is y times or y trans maybe okay y is this way. Y times C1 this thing. So for user 1, the corresponding code is C1. For user 2, corresponding code is C2. So at the receiver end, when the users will receive the signal, they will do correlation with whatever their CDMA code is. And it will do zero padding for the terms that don't exist. So for user 1, the correlation is y times C1 transpose. So this will be 0.5 minus 0.9, 0.4, 0 times C1 transpose. So what we will have is C1 is 1, 1. So I'll just multiply this with 1, 1, and there are two more terms. So which, well, like, we'll just assume zero padding because that's what we do. That's what is done. That for the remaining coefficients that don't exist, just assume a zero padding. So what does this correlation give you? This gives you 0.5 times 1 minus 0.9 times 1. So this gives you a negative correlation minus 0.4. Okay. And for user 2, what you'll have is y times C2 transpose. So C2 is 1 minus 1. So same formula, minus 0.9, 0.4, 0. And C2 is 1 minus 1, 0, 0. So this will give you 0.5 plus 0.9, right? To multiply this, 1.4. So you can see that user 2 will have a higher correlation than user 1 because you transmitted C2. So that is your kind of a check, you can say, that since you transmitted C2, then user 2 will have higher correlation. If you would have transmitted C1, then user 1 would have higher correlation. So that is how CDMA is done. Is this clear? Any doubt? Okay. So this is done. Then go to another.
Excuse me, am I audible?
Yeah, you are.
Yeah, I just have one doubt. We said small n goes from 0 to capital N minus 1.
Yeah.
Then why y3 is required? Because capital N is equal to 3.
Yeah.
So n minus 1 is equal to 2.
Oh, okay. Yeah, you are right. I made a mistake. I mean, it won't affect the answer, as you will see.
That's right. But I just wanted
Yeah.
clarification. So
Yeah,
we
yeah,
should
this will be
calculate
true.
only y0 to y2 up to y2 only. Why y2?
Yeah, you are right. Y3 anyway, you can see that it came to be 0.
Yeah.
So you are right. So then this is yeah. So yeah, we can kind of edit everything. So then Yeah, then you'll have, this becomes even more simpler. Answer stays the same. So that is actually anyway n1 plus n2 minus 1. That is the minimum support line. And whatever is beyond that anyway comes out to be 0. So doesn't matter. But still.
But when
Yeah,
we
that
have
is,
longer code, then maybe it is the right
yeah, I mean
number.
you'll just have a bunch of extra zeros. But yeah, you are right. Like I made a mistake.
We should calculate only up to yn minus 1.
Yeah.
Thank you.
So, I was using Microsoft OneNote earlier, but it's causing some problems with the audio issues. But anyway, I'll try using this. So okay. So yeah, this you are absolutely right that this capital N I calculated to be 3 and I'm summing from 0 to n minus 1. So this summation I would only have to calculate up to y0, y1 and y2. y3 was not needed. y3 anyway came to be 0. So yeah, let us continue. Now, okay. So then another type of kind of long form problem is with this interference and voice activation factor. So let's take that kind of question. So you are given multi-cell CDMA system, where you're told that the out of cell interference IO, C is something like 0.5 times the intracell interference, right? I, C. So this is something that we're told.
Excuse me?
Yeah.
Is it possible to see the complete problem statement and then we try to solve it?
Yeah. No, that is what I'm doing. I'm writing the problem first and then solving it, right? So step by step, I'm doing that. So you have, like, I don't have it written, but I'm just kind of writing step by step. You have a multi-cell CDMA system. I think this is clear, right? You have like multiple users, multiple base stations, then like each base station is its own cell. And so in a particular cell, you are told that in like out of cell interference, like in inter-cell interference is 0.5 times, half times the intracell interference. And you are told that length of spreading sequence is 64 in CDMA, and this ratio, interference to noise power ratio, is 6 dB. 6 dB, right? And you are told voice activity factor. So like this called voice activity. So this is there in the lecture, but I'll just right. Voice activity factor nu is given to be, let's say 0.2, right? Okay. So, and you are told that number of users, like number of users in a cell, per cell, number of users per cell, which is denoted as capital K, equal to 100, let's say. I've taken some random numbers. So, and you are also told to assume perfect power control. What does that mean? So for that you mean mod alpha K equal to 1 for all K. For all users, your channel gain, your power control is such that you have adjusted it such that channel gain is same for all users. So that is, your perfect power control. So now you are asked, what is the SINR of the system? Signal to interference plus noise ratio. Now this is again a very formula-based question, and now I can derive the formula if you want, but then that derivation is already there in the lecture. But I can kind of try and give an intuitive idea if you need. But essentially, the formula for SINR in these cases, so this quantity is denoted as alpha, right? This, you are told that this out of cell interference is some factor of intracell interference. So this factor is denoted as alpha. So then I can essentially what I mean is this alpha is equal to 0.5. And so SINR actually, like, you can compute the formula for it to be 1 by 1 plus alpha times mu, which is the voice activity factor, times capital K by Q, 1 plus noise variance divided by interference term of a single user. So this is actually the formula. And so again, this is very simple question. You just have to put in the formula and do. The only thing you have to be careful again is this noise race factor, or I naught by N naught, interference to noise power ratio. You have to check whether it is in linear scale or dB scale. So you are told here in this problem that I naught by N naught is given to be 6 dB. So 6 dB, which in linear scale is approximately equal to 4. Right? So this is the only thing that you need to just carefully maneuver. Right. So now all you have to do is just put in the formula. So N naught by I naught is 1 by I naught by N naught. So that's this, right? N naught by I naught is 1 by 4. And so now you just put, so can somebody calculate and tell me? See, 1 second. So alpha is 0.5, 1 divided by 1 plus alpha, so that is 1.5 times voice activity factor is 0.2. 0.2 times number of users 100 divided by 64 into 1 plus 1 by 4 or 5 by 4. Not, so you can calculate and kind of do the mathematics, but this is very easy. So this will be SINR, and maybe if your options are in dB, then you have to calculate from linear back to dB scale, which you can do, I think. And so you will get some
Sir,
answer.
linear means we have to take 10 log 6, na?
Which one?
This 6 dB.
Yeah. You will have to take 10 log. No. 6 dB is dB. You are already given in dB. So when you are converting from linear to dB, then you take 10 log of that value.
Yeah, 10 log of 6.
This is the other way.
So
This we are converting from dB to linear. So this will
yeah,
be 10 into 0.1 times 6. Sorry, 10 to the power 0.1 times 6.
yeah, 10 to the power 0.6. Right.
This is the other way. It comes to be 4. Almost 4. So you can just do the calculation and compute SINR. So that is just like calculation only. And for same system, let's say you are asked, what is the pole capacity? Pole capacity, K pole. So pole capacity is like, what is the absolutely maximum number of users you can accommodate? Like you have no bound on interference. You can allow interference to go as high as possible, but even then, like you have a certain capacity. So So what is that capacity? This is also again like as far as problem solving is concerned, this is a simple, the formula is there. And so you can just, okay, so sorry, pole capacity, K pole is defined, let's say for a SINR target equal to, let's say, 10 dB, right? So what does this mean? This means that I need my target, like my target is that at receiver I should get 10 dB SINR. For that, what is the maximum, like if I have no bound on how much interference like I can allow, then what is the maximum number of users I can accommodate? So then for that, the formula actually comes to be K pole equal to Q by SINR target times 1 plus alpha times nu. So again, values are known. Q length is 64. SINR target is 10 dB. You have to convert to linear scale. So this you need to be careful. 10 dB in linear scale is, luckily, it is 10 dB in linear scale is 10. Right? So 10 dB in linear scale is 10 and 1 plus alpha. So that is 1 plus 0.5. Alpha you are given 0.5 and voice activity factor is 0.2, I think. So you just have to calculate and tell me the answer. I believe what will be the answer. You have to round up, do some rounding up, because this might come out to be like, yeah, this might come out to be non-integer. So you have to like take a floor or something. So how much will it be? 1.5 into 0.2. So
It is 21.
21. Okay. Okay. Yeah, I can calculate also. 1.5 times 0.2 is 0.3. So 64 by 3. Okay. Yeah, 21. Fine. So pole capacity for this kind of target SNL is 21. Right?
That means we ignore the factor 1 plus N0 by I0 in the above equation.
Yes. Yes. We ignored the factor because we are allowing, let's say, theoretically, let's take interference to go to infinity or something. So then interference per cell, let's take it per user, let it go to infinity. So then, yeah, like that is kind of extreme case. So then this will go to 0. This will become 1, right? 1. N0 by 0 will become 0. So this will become 1. So that is like extreme limiting situation. Okay. Now, now for the same question, you are told, let's say same SINR target. You still have a 10 dB SINR target. And you want to say, and you are told that total noise rise, which is total noise rise is given to be so you have same SINR target, same value of alpha, same value of voice activation factor, same value of Q, and you are told that total noise rise due to interference is 6 dB. So now you are asked what is the practical capacity? Okay. In this question, capacity is not log of 1 plus SINR, but by capacity, we mean how many users can be supported in a cell. So let's step back a little bit. Firstly, what you are told is you are given the number of users per cell and you are asked to calculate the SINR. And if you calculate this SINR will be probably some very low value, right? Now, Now you are told that, okay, you have some SINR target and you have no cap on the interference. You can allow the interference of each user to rise as much as possible. What is the extreme limiting number of users that you can accommodate? So that is 21, which is, you can see that it is much less than 100, whatever we have taken initially. Now you are saying that you don't want the noise rise to be beyond 6 dB. What is noise rise? Noise rise, total noise rise is nothing but N naught plus I naught divided by N naught. So noise plus interference divided by noise. So this is like CDMA receiver has this problem of noise rise, that it amplifies the noise. And so how is the noise amplified? By this factor, noise plus interference divided by noise. So this you are told that it is 6 dB, which approximately is equal to, in linear scale, 4. So from here you have to actually do some calculation. And so here if you see I naught equal to 4 times N naught minus N naught. So this is 3 times N naught, right? Which means SINR is what? EB by N naught plus I naught. And I naught is 3 N naught. So this becomes EB by 4 N naught, essentially, right? So in other words, let me just write it again. SINR equal to EB by, because I naught is 3 N naught, so SINR becomes EB by 4 N naught. Or in other words, my bit energy will be 4 N naught times SINR. And I need to substitute it somewhere. Where will I substitute it? So this kind of relation I have between, and so SINR target is known, right? We have the SINR target, and we know the formula for this thing, right? Like you can again see it from the lectures. Interference per cell, total interference is given by this formula, right? That EB times this thing, 1 plus alpha EB times 1 plus alpha nu K by Q. So this is the formula for the interference, not normalized, just the interference. So you have the energy per unit bit, then you have this, because of scrambling sequence, you have this 1 by Q factor. Then you have this 1 plus alpha factor because of intercell plus intracell, like intracell plus intercell interference. Then you have voice activity factor and number of losers. Now, what you are asked here to find is K. So what is K? K is, okay, actually, let us step back a little bit. I naught is given to you as 3 N naught. You have calculated. So actually, the target here is to eliminate this N naught quantity, which we don't know. So 3 N naught is on this side. And on the right hand side, you have EB expressed as 4 N naught times SINR target. So you will have 4 N naught times 1 plus alpha times gamma K by Q times SINR target. So N naught and N naught will cancel out. And so what you will get is your practical value of K is nothing but, see, N naught and N naught cancel out. So you'll have 3 by 4 times Q by 1 plus alpha times nu times SINR target. SINR target. And if you see that this quantity is the same that I had written here. Q by SINR target 1 plus alpha nu. Same thing. So this is nothing but K pole or pole capacity. So your practical capacity K is some factor which is less than 1. So in this case, 3 by 4, 75% of the pole capacity. Because you want to have some practical bounds on the amount of interference that you will allow. So then K pole you have already calculated to be 21. So 3 by 4 times 21, what will it be? Actually, like if you are absolutely accurate, then K pole was 64 by 3. So this is nothing but 3 by 4 times 64 by 3. So this comes out to be 16, right? So your practical capacity is 16. So that is the essentially summary. That initially that you have to first calculate pole capacity, and also then if you have some like limitation on how much interference you want to allow, then you will also then you have to calculate practical capacity. Pole capacity, practical capacity. So this is it. Let me know if you have doubts. Other than this, there is nothing to cover in this week actually. And on Sunday, I have my next session, which will be the final session. There we'll cover what is left. So I think MIMO is being covered. So I will cover that and problems related to that, and then then that will be the last. At least I won't need any extra session. The other teaching assistants might. So anyway, like any problems with this, I can go over it again.
This is okay.
Yeah.
May I ask something about the final exam pattern?
Okay. I am not setting the final exam. I'm not involved with all that. So I am my role here in this course is just to help with the course, and help students understand and solve the assignments. I don't have access to like final exam or what is going on. So that you can ask on the NPTEL Swayam forums, but typically in this course at least, I think you can expect the final exam to be somewhat similar to assignment questions, like similar difficulty level or similar type of questions. So that much you can expect. Like you won't get maybe exactly the same questions, but something similar.
Generally, what percentage of total number of questions are numerical type and something
As I
like
said,
that?
I'm not involved with that, so I cannot answer the question. You'll have to ask in the course, in the
No,
forums on.
that may vary from subject to subject.
Yeah.
Thanks for the session.
Okay. Anything else? Okay. Then I'll end the session early.
Sir,
Sundays usual. Yeah. Tell me.
sir, how this SINR has come, SINR target has come
So
in this
it is given in
formula of I0?
it is given
No,
in
in
the
formula of I0, sir, here.
not in formula of I0. See, I0 is calculated from
Okay.
this thing. So
We
you
are
are told
getting
that
3
your
and 0.
noise rise is 6 dB. So because of interference, you have 6 dB noise rise. So then so that is from where you are calculating your I0. So N0, so noise rise is this factor N0 plus I0 divided by N0. So that is 4. From there you calculate I0 equal to 3 N0. So for different values you can calculate. And from there you are calculating SINR in terms of EB by N naught. So now that you know that this is the noise rise target that you have, you put it here. And so you also have an SINR target. You have two targets. You want the interference to be bounded. So you have a noise rise target, and you also have an SINR target. So now you know your SINR target. It is typically given in the question. So 10 dB here you are given. So then you have to. So what you have to calculate is how much power you should transmit with. So EB you need to calculate. So that EB is 4N naught times SINR target. And so essentially then this is just, and from another formula, you know that I naught is, so for a multi-cell CDMA system, this is the formula for I naught, right? You have your signal power times this 1 plus alpha factor, because you have that I comma C plus I O comma C, right? You have intracell plus intercell interference. So then that comes out to be 1 plus alpha times I comma C. And then for intracell interference, you will have capital K other, K minus 1 is approximately equal to K. So K users, all of them will interfere. Not all of them will interfere, because some of them are active and some are not. How many of them are active? That is given by this voice activity factor, right? So you are told voice activity factor 0.2, it means that 20% of users are speaking. Like if you're in cellular communication, then like 20% of users are active. So then voice activity factor determines the interference. So you can just go through the theory, but this is very intuitive. That so then
Lastly, we
this
have
is,
got this 3N0 equals to
yeah,
4N0 into 1 plus alpha into gamma into K.
yeah. And so okay, you are asking how this SINR target came. I have just substituted this EB equal to,
Okay.
yeah. So I
Okay,
just
okay.
substituted this here.
Okay, sir. Okay, got it.
Yeah, yeah. So then you just eliminate N0 and then you calculate K. Very,
Yes. Eliminate
you're
N0.
eliminating N0. You're eliminating.
Yeah. That is okay, sir. Okay, sir.
And that is all that is there. So this is again very mechanical kind of question. Okay. Anything else? Okay. Then I'll end the session. Okay. Bye.